All right, so taking a look at example 11. Water is being pumped into a conical tank at the rate of 15 meters cubed per minute. If the height and radius at the top of the tank are 12 meters and 6 meters respectively, find the rate at which the water level is rising at the instant when the height is 4 meters. So we have a cone. We have the water in there that is rising. And we know that we're going to have, for the cone, a radius, and we're going to have a height. Now, at the very top, it says that the radius is 6 meters and the height is going to be 12 meters. We also know that in this case, because it's a cone and not a cylinder like the last example, that the radius and the height are both going to be changing as the water level changes. Now, in the last example, our radius was a constant. The radius isn't constant anymore. So, thinking of what we know that we're dealing with the volume of a cone, which is 1/3 pi r squared h. Once again, we have 4 variables. The volume, the radius, the height, and time. Now, because when we look at the radius and the height, we could pull it out and we know that even though they're changing, they're still creating this right angle triangle where the angles inside aren't changing, which means that the ratio of the radius and the height have to stay the same. If the angles don't change, that ratio stays the same, just like what we learned in trigonometry. Which means that in this case, if the ratio of the radius to the height is 6/12, then that means that the radius is going to equal, when I multiply the height to the other side and reduce that fraction, 1/2 of whatever the height is. That's always going to be true, no matter what. Now, we also know, given the information, that we have the rate that water is being pumped into the tank, so it's positive. The volume over time is going to be 15 meters cubed per minute. We know we're doing this for when the height is 4. And the other thing that's really important to note is it wants us to find the rate at which the water level is rising which means what I'm trying to solve for rising is dH over dt. Now, one thing is that we, one, don't know the change in rate of the radius over time, and two, it's not actually what we're trying to solve, which means that in this case, where we saw like what are the steps that we have to do, step 4 says eliminate variables. Well, this is where that's going to apply. If my volume is equal to 1/3 pi r squared h, and we know that r is always going to be 1/2 of h, then the volume is going to equal 1/3 pi and 1/2 of h squared times h. Or the volume is going to equal, when I square that out, pi over 12, and then h squared and h is going to be h cubed. Now, if we had differentiated from here, we're going to wind up with a dv over dt, a dH over dt, and a dr over dt. But we don't really want dr over dt in this case. It's not really applicable to this question because even though we have the radius, we can solve what that is in relation to h because they're changing at this set rate. So what I am going to say is when I differentiate this, dv over dt is going to equal pi over 12, and the h cubed is going to equal 3h squared times dH over dt. This is all when h is equal to 4. So when I sub in my values, I know that 15 is equal to pi over 12 and 3 times 4 squared times dH over dt. Now, it wouldn't have been wrong if you want to and simplified this and divided the common factor of 3 out of there to change this into a 4. That's fine. We're going to wind up doing the same thing here anyways. We also know that we're going to be multiplying by 4 squared and dividing by 4, which means that we could even do that again and cancel out a 4 from here and a 4 from here, which means what we actually have is 15 is equal to 4 pi and dH over dt. So dH over dt is equal to 15 over 4 pi meters per minute. So the water level is rising at a rate of 15 over 4 pi meters per minute when the height is 4 meters.